All right, so we've done in section 4 triangle congruence. We talked about different ways or shortcuts to prove that triangles are congruent. Today we're going to learn about two more. So the ones we've already learned are SSS and SAS. Today we have two more. It's ASA and AAS. Okay? So the first one is ASA. And here we have another configuration. So we need angle, side, angle for this one, ASA. And it says that if two angles and the included side of one triangle are congruent to two angles and the included side of a second triangle, then the triangles are congruent. So basically, what does included side mean? If I have an angle here and an angle here, then the included side is the one that connects the two congruent angles. Okay? So included side.
How do you know that side is congruent to the other?
Is the side that connects the congruent angles. So what the theorem is saying is this: if two angles are congruent to two angles here, and the side that connects them is congruent to the side that connects them here, then no matter what, okay, the triangles are going to be congruent. Okay? So in this case, I have triangle WTR congruent to triangle what? HGC. So let's prove one using the ASA postulate. So sometimes you can prove triangles congruent using a couple of, right? So sometimes it could be ASA and SAS. It could be ASA and AAS. And if it says to prove it using a specific postulate, we have to be mindful of that. Okay, we're told that CP bisects angle BCR and BPR. So if CP bisects angle BCR, I immediately go and mark down that the two angles here are congruent. And if it also bisects BPR, then these two are congruent. Okay? Now, we need to prove that triangle BCP, which is this one, is congruent to triangle RCP, that one. Okay? Here, I'm told CP segment bisects angle BCR and angle BPR. Now, the next step is, okay, what do I get from this? Well, the fact that it's using the word bisects means I have congruent angles here. So angle BCP is congruent to angle RCP, and also angle RPC is congruent to angle BPC. And what reason would I give for this? Definition of angle bisector. Right? So it follows directly from the step above. So what I have now is I've shown that there is an angle that's congruent. I've shown there is another angle that's congruent. So that's A and A. What I need now is a side. So if I need ASA, these two angles are congruent. Now I need the connecting side, which is this one. Already we know that since it's being shared, it's congruent. So I say CP is congruent to CP segment. What's the reason? Reflexive. And this is my side. So this is now ASA. Therefore, I can now very easily say triangle BCP is congruent to triangle RCP, SAS congruence. I'm sorry, ASA congruence. Yeah. The next one is angle side angle congruence, or AAS congruence. And this says two angles and a non-included side of one triangle are congruent to the corresponding two angles and a side of a second triangle. Okay, so basically I have two angles here, but the side that's congruent is the non-included side. So it could either be this one, or it could have also been this one. Okay? So let's just look at what we've gone over so far. We had SSS, which is just talking about sides. And we had SAS. Okay? What else did we have? In this section, we had ASA and AAS. Let's compare ASA and AAS for a minute. ASA is saying that I need two angles and the side that's included. AAS is saying that I need two angles and the side that's not included, meaning it could either be this one or that one. So what's the moral of the story? If you have two angles, okay, no matter what side you have with the two angles, you can prove that the triangles are congruent. Okay? So any two angles and one side is enough to prove triangles congruent. Okay? Any two angles and one side is enough to prove congruent triangles. Alright, so in this case here, the two triangles that are congruent are triangle JKL and which one? Triangle CAB. Okay. So here it says to write a two-column proof, and if it doesn't say what congruence postulate you're supposed to be using for it, then it's up to you. Okay? Okay. So, we have here RQ is congruent to ST, and they're also parallel. Remember that when it talks about parallel lines, it's sort of a cue for you to look for alternate interior, consecutive interior, and so on. Okay? So look for alternate interior, consecutive interior, and so on. Okay, so let's write this down first. RQ is congruent to ST, and RQ is parallel to ST. Okay, so here we already have a congruent side. I want to prove triangle RUQ, this one, and triangle TUS, which is this one, are congruent to each other. Okay. So what do I have? What else do I have that's congruent here? Right. These are congruent because they're what? Vertical angles. So angle RUQ is congruent to angle TUS because vertical angles are congruent. You can, I just, by nature, I try to be consistent, but you can for angles. It's the triangles that you want to get in the right order. Okay, so what else is congruent here? What about this one? Is this angle S congruent to anything? Which one? Q, Y? Alternate interior angles. Angle S congruent to angle Q because parallel lines, implies alternate interior angles are congruent. So here in the second step, that gave me an A. The third step gave me another A. What do I have now? Is this AAS or is it ASA? It's AAS, right? Because it's angle, angle, and the non-included side. Okay? So it's angle, angle, and the side that is not in the middle, that's AAS. So number 4 is going to be triangle RUQ is congruent to triangle TUS, AAS congruence. All of the AAS, SAS, SSS postulates are good reasons.
It's weird because it's like jumping all the way to the conclusion.
Right, but that's enough because you're told, just like you're told, that if two lines are perpendicular, then you can immediately say that the angle is 90. If you've got this configuration of AAS, then immediately the triangles are congruent. Okay? You've satisfied the hypothesis, so the conclusion is true.
So it would be ASA if it was UQ and TU.
Right. If it was the angle in between, it would be ASA. Okay, so here is a summary of how to prove triangles congruent. So we learned about SSS, SAS, ASA, AAS, and you've got a really good summary with diagrams too. It's a good idea to just have this diagram somewhere handy. You can look at it. They do a good job of putting down these configurations here. So one thing to remember is that these 4 are, you can apply them to any triangle, okay? These apply to any triangle, okay? So whether it's acute, obtuse, right, equilateral, scalene, you name it, all of these 4 can be applied to all triangles. Now, there is one more way to prove triangles are congruent. Okay? But it only applies to right triangles. Okay? So suppose you had a different configuration here. Suppose you had, so here you have an angle on 2 sides, but look at how it looks. It's the sides and the angle in between. What if, let's take a look at this one. If you had an angle and 2 sides here. Okay? So that's not one of the ones we've done so far. Okay? An angle and 2 sides. It turns out there is no way that that will work. So if you have an angle and 2 sides congruent, you can't prove that the triangles are congruent, except if this angle was a right angle. Okay? So this only works if the angle is 90 degrees. Okay? So how would you remember that? So this gives you ASS or SSA if you look at it from the other way, right? Okay, you think there will ever be a proof or a theorem in geometry with that name? I doubt, right? So whenever you want to write, whenever you get the urge to write down ASS or SSA, which spells the same thing backwards, resist that urge. It doesn't exist. Okay? So the alternative to this, if the angle is 90 degrees, then you have a right triangle. It's called the hypotenuse leg HL theorem. Okay? So this says that if the hypotenuse and a leg are congruent to the hypotenuse and the leg of another triangle. Okay? So basically, you have to have a 90 degree, and then the hypotenuse and one of the legs have to be congruent. All right? So this is the only one that only applies to right triangles, However, can you use one of the ones on top for a right triangle? Absolutely. Okay, so ways to prove triangles are congruent. What do we have so far? SSS, SAS, ASA, AAS, and HL. Okay? So these 5 ways. And that's it. This is the only one. All right. So what do we have here? Let's see. We have a right triangle, right? But is this HL? No, it's one of the other ones. So we have an angle, and an included side, ASA. Okay? Here, we have 3 angles congruent. Does that work? No. Right, one could be bigger, one could be smaller, so no sides congruent. So this is not possible. What about this one? I have a side, and I have another side. Is this SAS? If it was SAS, then it would have been side, included angle. This, well, SSA spells what backwards? So it's HL. Okay? So when you do get SSA with a right triangle, then it's HL. So what I have here, if this is the right triangle, this is the hypotenuse and a leg. So this is hypotenuse leg. Because when you don't have any sides congruent, then you cannot prove that triangles are congruent. If you have if all 3 angles are congruent to all 3 angles, it could be, they could have very different sizes but still have congruent angles. Okay. Now for the grand finale, and this is a grand finale. So watch this proof. So what's the longest proof we've done so far? How many steps? 7, 8. Do I have a 10 one? 7 or 8, I think, is what I remember. Okay. All right, so let's see. We have AB parallel to DC. And we have AB perpendicular to BC. And we have that E is the midpoint of AC and BD. So these parts are congruent. These parts are congruent. What I have to prove is that AC, which is this long one, is congruent to which one? BD, this one. So this is what I want to prove. Okay? Now, here's the plan of attack. Okay? Oh, it's a science lesson and a math lesson in one. This is how colors combine. See? I could go 3 hours on that. Okay. So, here's what we're going to do first. Basically, at the end of the day, I want to prove that this big triangle is congruent to this big triangle. Okay? And then I could say CPCTC for the long diagonal lines. Okay? So this big triangle congruent to that big triangle. To do that, though, first, I have to prove the little ones are congruent, and then go to that step. So, I'm going to prove that the little triangles are congruent. I'm going to use that to get sides to prove the big triangles are congruent. And then I could prove that those 2 sides are congruent. So let's go. Hang on. All right. Okay, so that's a long ways away. Okay, so here we have AB parallel to DC, AB perpendicular to BC, and E is the midpoints of AC, BD. This is AC. All right. Now, I can prove, all right, since I have the midpoint, I can show that AE is congruent to CE. And BE is congruent to DE. Why? Midpoint theorem, you're right. It's not definition. Okay. Now, I have angles here that are congruent. So angle AEB is congruent to angle CED, vertical angles theorem. So, same. When you say vertical angles are congruent, you're just saying the contents of the theorem. So here I have two sides and an angle, and they're configured as SAS, so I can say triangle AEB is congruent to triangle CED, SAS congruence. Okay, next. So now I've proven that those two triangles are congruent, okay? This one and this one are congruent. So remember, let's keep our eye on the ball. What we're trying to prove is the big ones are congruent, okay? To show that the big ones are congruent, now I want to show that this side is congruent to that side. Can I say that? If these two triangles are congruent, then the corresponding sides are congruent because of what? If triangles are congruent, sides are congruent because of CPCTC. So I can now say AB is congruent to DC, CPCTC. Next. This side is being shared by the two big triangles. So that's the fourth one now. BC is congruent to BC because of reflexive property. Okay? Now, for number 7. How big is angle ABC? It's a right angle, right? Why? Because those two lines are perpendicular. So I say angle ABC is a right angle. This is the definition. Well, not definition. Perpendicular lines form right angles. Okay? I guess. Okay, so number 8. Now, these two lines are perpendicular. I'm sorry, these two lines are parallel. If this is perpendicular to one line, it's also perpendicular to another parallel line, remember? So for number 8, we're going to say, sorry, for number 8, we're going to say BC is perpendicular to DC. And this one, I have the theorem here from the last packet. It's the perpendicular transversal theorem. Okay? So perpendicular transversal theorem. Now, if it's perpendicular there, then what do I know about that angle?
It's also 90.
It's also 90. So that's angle DCB is a right angle. By the way, we can combine this and this. Okay? You can combine this and this if you say this one first. So if we say this one first, then you can combine 7 and 9. But this is fine as well. So this is perpendicular lines form right angles.
But it has to be with parallel line, as in to say the perpendicular line.
Right. So now, what do we know about angle DCB and angle ABC? They're congruent. Why? Because all right angles are congruent, remember? So now what I have here is SAS. SAS. Okay? So I can say triangle ABC, this big triangle, is congruent to this triangle because of SAS. Okay, so here we have S, S, and an angle in the middle. So, triangle ABC is congruent to triangle DCB, SAS congruence. And if the two triangles are congruent, then their sides are congruent because of what? CPCTC. So, AC is congruent to DB, CPCTC. And there you have it. We're done. Okay? 12 steps only. All right, so this homework, along with the other one for section 4, is due in the next class.